we don't really have a way to compare earthquakes in one part of the world with another. I mean, of course, we have a way of measuring these events and giving them a number that translates to strength, but our methods are kinda shaky. Earthquakes like the one that hit New Jersey in early 2024 can feel like a bigger deal than ones that are technically the same strength in California, and it's not just because of their novelty. It turns out that earthquakes in the eastern US really do go farther and hit harder than their western counterparts, and it's all to do with the rocks they encounter along the way. So here is how earthquake waves are fundamentally different in different places, and what makes our measurements way less meaningful than you might think. Let's start out with the fact that we are not all working with the same scale. Earthquakes happen when rocks break and slip along geological faults, releasing energy that travels through the ground as seismic waves. These waves are recorded by appropriately named seismographs, which show how much the Earth moves at that particular location. Then, that measurement can be used to calculate the strength of the quake. One of the most famous measures of earthquake strength is the Richter scale, which was developed back in 1935 by the American seismologist Charles Richter. It is an objective measure of the earthquake's magnitude based on the height of the tallest peak on a seismogram. It's also logarithmic, meaning that a quake measuring 6 on the Richter scale is 10 times stronger than one measuring 5 and 100 times stronger than magnitude 4. But the Richter scale isn't as objective as you might imagine, because Dr. Richter devised this scale using only data from a single type of seismograph in California. Most of the earthquakes in California happen at a similar depth and behave in a similar way, so the calculations worked locally, but couldn't fully capture the behavior of earthquakes elsewhere around the world, which is where most earthquakes happen. So if you read about a magnitude 5 earthquake today, they probably don't mean magnitude 5 on the Richter scale. Instead, it is an earthquake with a moment magnitude of 5. Helpfully though, it is actually pretty similar to the Richter scale. The moment magnitude is a more broadly applicable measure, calculated from several different seismograph readings. And it is related to the physical properties of the fault that caused the earthquake, including the rigidity of the rock, the size of the fault that slipped, and the amount that it slipped by. The numbers are then converted into a scale that closely mirrors the Richter scale to be consistent with that famous but flawed magnitude measurement. It's just a little trick that we played on everybody. Everybody thought that we're still using the Richter scale, but we're not anymore. And yet, despite the improvements made over the years, even the most objective measures cannot paint a complete picture of earthquakes in every region. Quakes of similar magnitude can have very different effects depending on where in the world they occur. For a start, the rocks that seismic waves travel through have a big effect on how far they'll go and how far from the epicenter you'll feel them. It's a bit like sound waves traveling through solid materials. Compare the ringing sound that goes for ages when you strike like solid metal to the bonk that you hear when you hit a piece of wood. And if you whack a rotten piece of wood, that thunk tells you that those sound waves aren't getting very far at all. And this is a similar situation between the east and west coasts of the US. On the east coast, the geology is old, solid, and continuous, and the seismic waves travel great distances with ease. As a result, shaking can be felt from much farther away. In comparison, the west coast sits near a tectonic plate boundary, and the bedrock is all convoluted with lots of cross-cutting faults. So the seismic waves are slowed and attenuated, and shaking isn't felt as far. So in 2011, shaking from a magnitude 5.8 quake near Mineral, Virginia was felt over 950 kilometers away, while in 2014, a magnitude 6 earthquake in Napa, California was only felt 402 kilometers away, despite releasing about twice the energy of the Virginia quake. So even when different earthquakes are measured on the same scale, an almost magnitude 6 earthquake in Virginia is going to spread out to a totally different maximum distance than a magnitude 6 earthquake in California. And it's not just the US that experiences this quirk of seismic transmission. The Gujarat earthquake in India in 2001 had a moment magnitude of 7.7 and resulted in a huge death toll of 20,000 people, with over 150,000 people injured. It was what's known as an intraplate earthquake, originating from a previously unknown fault within rocks that are compressed. As a result, shaking was felt over 1,000 kilometers away in the capital, New Delhi. In comparison, the Sumatran Andaman earthquake, which caused the devastating Boxing Day tsunami in 2004, had an estimated magnitude of at least 9.1. But while the tsunami caused widespread devastation, the shaking from the quake was felt mostly in line with the fault that slipped. Despite being much stronger than the Gujarat quake, shaking from this event was barely felt in Malaysia, 600 kilometers away. But local geology controls more than just the distance that seismic waves travel. It also affects the intensity of shaking wherever they happen to hit. So some earthquakes feel bigger than their magnitude rating might suggest. In contrast to the objective magnitude at its epicenter, intensity is a subjective measure of an earthquake's strength. In the US, it's classified on the 12-point modified Mercalli scale, ranging from 1, not felt at all, to 12, extreme shaking. In general, being closer to the epicenter means you will feel more intense shaking for any given earthquake size. But it's not always a straightforward relationship, because areas that are underlain by softer sediments often experience much more intense shaking than those with a solid bedrock underground. That's because seismic waves travel slower through soft sediments, but at the same time, they increase in amplitude. The waves can also kind of bounce back and forth between sedimentary layers, so the shaking goes on for longer. You can think of it almost like a bowl of jello on a table. If you hit the table leg, the tabletop will move a little, but the jello will jiggle for much longer and much more. This is another reason that earthquakes on the North American East Coast often seem more intense. There are many areas of Washington, D.C. that are underlain by sediment, and so experience this jello effect, resulting in more damage than you would expect from a relatively small earthquake. Local sedimentary effects are not unique to the U.S. East Coast, though. On the West Coast, the whole of Los Angeles Basin has around 10 kilometers of sediment underneath it, and can experience shaking 5 times more intensely than in sites in the surrounding mountains. And a similar process leads to higher intensities of shaking all around the world. Notably, the 1985 earthquake near Mexico City shook the capital to its core because the city is built on an ancient lake bed. And earthquakes in 2010 and 2011 in Christchurch, New Zealand were especially devastating because the city is built on the Canterbury Plain, underlain by gravel washed down from the nearby Southern Alps. In fact, our tendency to build towns on the flat, soft grounds of plains and basins rather than in the mountains hasn't done us any favors when it comes to amplified earthquakes. Geological amplification causes a kind of intense, high-frequency shaking that's particularly damaging to buildings right where we like to build them. So whenever an earthquake strikes, spare a thought for the ground underfoot. Magnitude can give us an idea of the energy released, but it's the geological context that really matters. And while there may be way more quakes in the US's mountainous west, the ones in the ancient sedimentary east are deceptively intense.